Okay, so we want to keep on the theme of wet bubble packings, and our next talk is going to be from Tudur Davies from here in Aberystwyth University. I think the talk is about modelling and coarsening in wet foams using the bubble model.
Thank you. Yes, so I'm going to talk about a much more simple model for modelling wet foam. I'm going to use the bubble model, which is a 30-year-old model. The bubbles essentially are soft spheres in 3D or soft disks in 2 dimensions. And so I know I've talked a bit about foams already. And so I'm interested in foams for many reasons. They're very complex materials. They have a highly nonlinear response to the stress applied on them. So at low stress, a foam can behave as an elastic solid, even though it's more than 90% gas in some instances. Okay, and it also evolves due to processes such as drainage. So here is a picture of a foam that has been drained. So you might think of the foam on top of a pint of beer. The bottom is very wet, and the top is quite dry. And so the shapes of the bubbles are different. A dry foam has bubbles as a shape as polyhedral cells with some curved surfaces. Down the bottom in the wet foam, the bubbles become more spherical. And so this is the type of foam that I want to model. And so it seems appropriate to make that approximation that bubbles are roughly spherical. There are other processes that cause a foam to essentially age. Foam will coarsen over time due to gas diffusion between films. And some films will also rupture due to these processes. Of course, probably you know that foams have a lot of applications. So I've been interested in modelling how foams can be used to transport objects, solid objects. So in the past, I've been interested in how dry foams carry particles and objects. And so I've used surface evolver, and that limits me to very small samples. And so we focused on ordered foams. But really in industry, the foams that are used to carry particles and objects are quite wet. Yeah, so we do need to move into this regime and consider wet foams. So for example, foam is used for flotation, to separate minerals from waste material and so on, for recycling, paper de-inking, and cleaning soil and so on. So in that case, foam is quite wet. So I want to consider large foam structures. And so we're going to use this simple model, Durian's bubble model, where, well, I'll start off by imagining this in 2 dimensions. So each bubble is a soft disk in 2 dimensions, and when bubbles overlap, there will be some elastic repulsion between these bubbles. The model, so there are 2 main forces, and the assumption that we're going to make, and this assumption has been made by others as well, is that at every time step, the sum of forces on each bubble is approaching 0. Okay, so there's some viscous drag force, and this elastic repulsion, and they both sum to 0 for each bubble. I should say a bit more about these forces. So viscous drag, clearly, if a bubble is moving, it will drag its neighbour with it. It's quite simple. The repulsion you can think of as a spring-like force. So the spring coefficient given here as sigma 0 times the average bubble radius. Sigma 0 is just surface tension. Well, we have a dimensionless measure of the overlap and the direction of the force. So for the simulations I'm going to show today, we're not going to impose a flow. And so this term, this average velocity, you can think of this maybe as the average velocity of neighbouring bubbles, that is reflected, okay, 0. In that case, this assumption that the forces approach 0 each bubble each time step, that simplifies to give me this equation here. So the bubble velocities are just a result from the repulsion forces, where mu0 is the viscosity parameter. So we arrive at a timescale, dynamical timescale for the simulation. So we set this timescale, this ratio between viscosity and surface tension to be 1 in the working group presented. So we can model how the soft disks move, and I noticed a couple of notable contributions who worked with coarsening using the bubble model. So Gardner did this 20 years ago. More recently, Brian Tighe's group in Delft have modeled coarsening. So this is not new. I'm using their work as inspiration and learning how to build the bubble model essentially. I'll discuss where I want to go on from there later. So gas will diffuse from one bubble to the other. And direction of diffusion depends on the pressure in each bubble. So bubble with a smaller number of neighbours tend to have higher pressure. And so what you tend to see is that a small bubble in this coarsening process will get smaller, large bubble will get larger. And so the rate of change of volume is given by this differential equation, where I just notes the label for the bubble, J is its neighbour. Okay, so the coarsening, the diffusion process happens across the contact surface area, or in 2D, just this length that I've drawn in blue. Finding that is just a simple geometrical calculation. So clearly, there's another time scale at play here. For the coarsening process, we want this to happen much more slowly compared to how bubbles rearrange, how the foam flows. And so we choose the diffusion parameter to be very small. So K is the diffusion parameter for the coarsening process. And so the second timescale that we have is the coarsening timescale. So I set K to be small, essentially so that the coarsening process, roughly speaking, happens at least 1,000 times more slowly than bubble rearrangements. So set up the simulation, we position n disks, thousands, tens of thousands of disks at random in its cell. The cell is periodic. But I ensure that there is enough space for the disks to move into without filling the plane. I then gradually increase the size of the disks until and relax the foam until we get to essentially a packing of soft disks, which is relaxed. Okay, so we stop this relaxation process once the energy is essentially converged to within some criteria. So that's how we set up the foam. We're now ready to turn coarsening on. So we haven't coarsened anything yet. So if we turn coarsening on and see what happens. So here I've got a couple of simulations. One is very wet form or bubbly liquid, where the gas fraction or the packing fraction is below the critical jamming fraction. Coarsening happens quite slowly there. But if you increase the liquid fraction, got the jam structure to begin with, there's more overlap clearly. The coarsening process happens more quickly. So you clearly see it's more obvious here. We have large bubbles, they've grown, and we have tiny bubbles which disappear. So we remove bubbles that fall and that shrink below a critical size, ensuring that volume is conserved. So clearly, this coarsening process is highly dependent on the liquid fraction or the gas fraction we set. But there are similarities between simulations that I've just shown you. If we consider the distribution of the disk size or the bubble size, there's a couple of regimes, I would say. So initially, the probability distribution of our disk size is essentially thin around the mean. So we set these disk radii from a triangular probability distribution. We could use a Gaussian. So it's quite thin. Over time, that distribution just broadens, but the mean bubble, mean disk size stays the same, roughly. After a while, we reach essentially a scale-independent state where the distribution of bubble size remains constant. Even though coarsening is still happening, bubbles are changing size, but the distribution of both sizes remains the same. So for the wetter forms, it becomes more and more apparent that we have a lot of very small bubbles appearing in our distribution. Okay, and thankfully the results for my simulations are very close to what previous groups have shown. If we consider what happens to the average bubble radius for different gas fractions, then we get this power law relationship in the scaling state. Well, clearly, we don't reach that scaling state for all liquid fractions, or gas fractions, as I should say. But for the forms that do reach this scaling state, the slope, this plot is roughly 0.45. And maybe surprising is how close that is to 0.5, which is the relationship that the scaling parameter for a dry form, which follows von Neumann's law. Now, von Neumann's law does not apply to wet forms, but nevertheless, it's quite close to what we're getting. We also record the number of bubbles. Remember, we delete the small bubbles, and so bubbles are lost. Clearly, this is more apparent in the drier forms. But this power law relationship, the number of bubbles over time, is now negative slope of 0.9. Okay, so that's what happens in 2 dimensions. We can also look at how jammed the structure is by plotting the coordination number over time. So the average number of neighbours of the bubble, and that gives us a bit more insight. So in the simulation that I've just shown, you might have noticed that some small bubbles just didn't really contribute to the process. They didn't have any neighbours. They just rested in the plateau borders. And so they are referred to as rattlers in literature, and they're omitted from our calculations for the structure. But what we see is essentially transitions between jam state and non-jam state during the coarsening process. Maybe the data to focus on is the green dots. And so that's an initial packing fraction or gas fraction of 0.87, which is jammed. After a while, as the coarsening process occurs, the coordination number falls below this critical value of 4. So it seems that the soft disks are filling up the space more optimally as they coarsen to this scaling state. So what I would like, so this is essentially work that has been done by previous contribution. What I would like to now go on is to model or to inspect the topological changes in a soft disk system. So T1s, we mentioned in previous talk. T1s are bubble rearrangements, so foams will flow, and that flow process is essentially bubbles rearranging. So here, simple example, soft disks 1 and 2 are neighbours initially, but after some time they might not be neighbours, and 3 and 4 have swapped to be neighbours. Okay, so you've got a neighbour swapping process. I'd like to detect this quite efficiently. So if somebody has some ideas of algorithms or software that can do this, then I'd be very interested to speak to you. So the idea that I had, you look at the changes in tessellation between a number of time steps. So here I've got a couple of configurations. So soft disks, you'll see are colored in black, but there are also another set of soft disks colored in red. That's really not clear because they're so close together, right? But there are some time has passed here, and there are a couple of examples where the tessellation has changed as a result of that evolution. And so that might indicate indicates the starting point of a T1 process of a neighbor switching, but in itself, it doesn't represent a T1. You know? So change in tessellation doesn't quite do the job for us. Now, I think we need to combine changes in tessellation with changes in the contacts. And so that is something we can easily detect. So here I've plotted gained contacts in green and lost contacts in blue. And there are many of these, and they don't represent T1s in general. But if we look at regions where all 3 are appearing close by, involving the same bubbles, then we might have topological changes appearing there. Okay, so if anybody has some ideas in this topic, then please do tell me. Okay, so one of the things I really like about the bubble model is the ease which we can move from 2 dimensions to 3 dimensions. And so now I'm doing exactly the same thing in 3 dimensions. I've got soft spheres in a periodic cell, and this is just the setup, the equilibration process. They're very small, and they're relaxed until we have the gas fraction that we want. So I'm using exactly the same model. Now I've got the simulation of 20,000 soft spheres. So to me, this is a very large sample, because we've studied dynamics over a long time. But I would like to work with larger samples. But so again, if people have ideas of efficient algorithms, software that we could use to do that, then that would be great. But broadly speaking, the same results apply in 3D. The distribution of bubbles sizes broadens over time. The growth rate is very similar. What I haven't done is I haven't modified the spring forces between neighbours. And in 2 dimensions, the spring-like interforces is a good approximation of what we want. But in 3D, that's not the case. In 3D, the number of neighbours a bubble has is important. And so, okay, this complicated expression is not so important for this talk, but this is what was proposed by Gardner et al. This proposal was based on a fit to surface evolver data. And so this is the next step, I would say, in my simulation. Try to get this to work and consider how does this affect the coarsening process. Okay, so here is where we are essentially. So, so I'd like to go on, modify the model, so to include processes such as liquid drainage. That will involve varying the stiffness of the spring between neighbouring bubbles. I'd also like to allow surface tension to vary with surfactant concentration, for example. I think that would be a nice modification to the bubble model, but there are lots of things I need to do before we get to that stage. Okay, and with that, I'll finish. Thank you.
Very nice work. As you go to the jamming point, gas transfer to the films becomes very small because the films become very small. But then you could also think of gas transfer through the liquid and the meniscus around the films. So this is something that becomes increasingly important as you approach the jamming point. Yes. Do you think there is? I know this is difficult, but do you think there is any hope of incorporating that into your simulations?
I think so. I think that's something that Gardiner tried to do. I think, yeah. So it's the next step. I would say. I think they've only done it for bubbles that have no neighbours. I guess that's what we need. So I know it's not. So that's a simplified version of what you suggested. Yeah. So I think it's possible, but something I haven't thought about that much.
Just one small comment. The Lacasse expression that you showed interpolates surface evolver data very nicely, but there is the more Switten theory. I guess that's more accurate, really. It would be a good thing to go in that direction.
That's a nice suggestion. Yeah. Yes. That's a nice idea. Yes. Thank you.
Are you planning to put a contact angle in?
Yeah, that's an idea. Again, I haven't thought about much because this is very new work for me. But yes, I think that would be a nice addition to the model. Something I will get my PhD to do.
Okay, it's possible. Yeah. Preliminary stuff, very sparse networks, of course, and I think that sounds interesting.
Yes. Yeah.
Maybe not very relevant to photos.
Right. Yeah. Reported on the last.
This is out of left field because it's not really about foam structures. It's probably about rheology of the wet part of the foam. I'm sure people have done this, but I could imagine a very careful experiment where you're adding the wet to the top and tuning it. So let's brain and then look at this as a population. Imagine people have done this with foam as opposed to solid things.
Yeah.
Just it's for anybody. What's the state of the art of this for you, for anyone else?
Right.
I'm just curious because I've heard for 35 years talks about training and I'm interested in the dry foam limit. I'm wondering what's known and done.
Yeah.
Sounds like a defense question.
Yeah, so I haven't done much with drainage. You're right, lots of people have worked on that.
Yeah, percolate, so steady state rain.
Yeah.
I'm not actually opening to anybody who may know. I mean, I think the guy sitting next to me.
Yeah.
Yes, well, what you described is called forced drainage in the community, and that's been studied a lot. It's an interesting thing because you've got a porous materials whose pore size evolves as the fluid penetrates into it. And this is a nonlinear evolution. And Dennis Ware has been working a lot on it, and he showed that there is a kind of soliton-like propagation that happens, and there's a lot of literature on that.
Okay, good. I hope so.
I can show you something.
Thank you. Thank you.
Right. Let's thank our speaker again.